In our last video, we used the Carnot cycle for heat engines to establish a definition for this new thermodynamic function which we call entropy. In this video, we'll look at a few definitions and take this definition a little bit further as it applies to the second law of thermodynamics. We start with the example of heat flow. Going back to our definition of entropy, where we define ds, changes in entropy, in terms of dq reversible, where we must be talking about the heat transfer for a reversible process divided by temperature. Now, if we have a situation where we're looking at heat flow between two bodies at different temperatures, T1 and T2, we'll let the heat transfer from body 1 on the left to body 2 on the right. The total amount of heat transferred we're going to call Q sub P. And let's take a look at how we would use our definition of entropy to determine the total entropy change for this particular process. It is going to be equal to negative Q sub P over T1, and that's because body 1 loses an amount of heat defined by QP. And then the second term, Q sub P over T2, corresponds to the amount of heat, or corresponds to the entropy change associated with the transfer of heat into body 2. So in this particular process, heat's flowing from body 1 at T1 to body 2 at T2, and these two terms in this expression correspond to the entropy change for these two bodies. Now, simply here, just a little algebra, we pull out the Q sub P term, and we're left with this expression for the overall entropy change. So the question is, this change going to be positive or negative? Well, if the body 1 on the left has a higher temperature than body 2, so the T1 is greater than T2, that means that the quantity 1 over T1 is going to be less than the quantity 1 over T2. And if that's the case, then this delta S term here is going to be greater than 0, because under those circumstances, the quantity in parentheses, if 1 over T1 is less than 1 over T2, the quantity in parentheses will be positive. So the overall change in entropy will be greater than 0. Now, of course, we know from practical experience that heat always flows from hot to cold, and this will be the situation that would be natural if, again, T1 is greater than T2. We know naturally heat's going to flow from body 1 to body 2, and we can see for this process that delta S for the flow from the hotter body to the colder body is greater than 0. Right, so this applies to the second law of thermodynamics. We're going to establish here, in the last video we talked about the Kelvin-Planck statement regarding the second law, which referred to a cyclic process. In this particular case, applied directly to entropy. We're going to say for an isolated system, as we saw on the previous slide, when the heat transfer from the hot body to the cold body had an entropy change greater than 0, that for isolated systems, the second law of thermodynamics says that delta S must be greater than or equal to 0. It is going to be equal to 0 in the case of an equilibrium process, and it's going to be greater than 0 in the case of any non-equilibrium process. If we consider the universe to be an isolated system, then we know that the second law may be summarized for the universe. For every process, delta S total for the universe must be greater than or equal to 0. One has to keep in mind here, of course, is that the universe consists of system and surroundings, and so that means that delta S for the system plus delta S for the surroundings must be greater than or equal to 0. And this, of course, means that it is indeed possible for delta S of the system for a process to be less than 0 if delta S for the surroundings is greater than 0 to the extent that its magnitude is greater than the change in the system. The important point is that delta S for the entire universe must be greater than 0 So let's not be confused here by this statement, as some people are. It is possible for the entropy change for the system to actually be less than zero. The process can still occur without it being a violation of the second law. So let's take a look at what happens to the surroundings and consider entropy changes in the surroundings. In this case, we will define the entropy change for the surroundings in terms of negative dq for the system, because if heat flows out of the system, it flows into the surroundings and vice versa. So whatever dq might be for the system, the dq for the surroundings will be in fact opposite, have the opposite sign. But the other important thing here is that whereas the system requires that we do the calculation for the reversible process, for the surroundings we don't have that requirement. And that is that because the surroundings are generally considered, we can rationalize this, the surroundings are generally considered to be so much larger than the system that any heat flow between the system and the surroundings is essentially reversible for the surroundings themselves. So we won't have this requirement that dq for the surroundings be for the reversible process when we do some calculations. This will become important when we do a calculation for phase changes in our next, in one of our future videos. So when we take this total universal change in entropy into account, where we look at the entropy change for the system, which is the first term here on the left, and then the entropy change for our surroundings, which is the second term, because we have this situation where ds for the surroundings is equal to negative dq for the system over t. We know the second law of thermodynamics requires that these two terms together must be greater than or equal to 0. And what that means then is that dq reversible over t will always be greater than or equal to dq system over t. They'll be equal to each other, of course, when the process is reversible, but in the case of an irreversible process, it's important to note that dq reversible over t will be greater than dq system for the actual reversible process. So again, dq system would be the actual dq for the reversible process, for the irreversible process, and dq reversible with that for an imaginary process that we have to devise to do the entropy change. This may be a little bit confusing right now, but we'll do some examples in a future video that will help clarify this particular statement. So again, because dq reversible over t corresponds to ds for the system, then we can see that under these circumstances that ds is therefore going to be always greater than or equal to dq system over t. And this is called the Clausius inequality. This will become important later on when we start talking about delta G, the Gibbs function for various processes. Let me add another point of clarification here, is that you notice that we don't use a subscript here on this ds term, and that's because we're just going to, when we're talking about changes in the system, we don't label it with a subscript. If it's not the system, we'll label it, for example, if we're talking about the surroundings, we'll label it with a subscript to indicate that we're talking about the surroundings. If the universe, will indicate with a subscript to indicate that we're talking about the universe. But if we have no subscript, you may always assume that we are doing the calculation for the system. Now, there's an alternative definition of entropy which we really won't explore very much this semester, but it was developed by Ludwig Boltzmann in the 19th century, and it's associated with probability. This alternative definition gives us entropy is equal to K, K being the Boltzmann constant, times the natural log of W, where W is the number of ways that we can achieve a particular state of the system. That is the statistical definition of entropy. It's interesting to note that Boltzmann's tombstone shows this equation on it. You might want to think about what kind of equation you would like to have on your tombstone. Pleasant thought. The statistical definition we can actually relate somewhat to the qualitative statement that we've always used with regard to entropy, in that it represents the amount of disorder in the system. In this situation, the more ways that we can achieve a particular state, the higher the entropy. Well, if you think about disorder, there are a lot more ways that we can generate a disordered state than an ordered state. Think about your room, for example. There are a lot of ways that you can move things about and make a very disordered, messy room, but there are only a few ways that you can organize things such that the room is in an ordered state. So there are far more ways to have the disordered room than the ordered room, so the disordered room, by this definition, has a higher entropy. It's also important to note that when talking about the second law then becomes a probability law. The second law says that, again, delta S for the universe for any process must be greater than or equal to 0. If we use this probabilistic definition of entropy, that simply means that there's a much higher probability that we go from an ordered state to a disordered state than vice versa. It does not mean that it is impossible to go from an disordered state to an ordered state. It is possible that we can go from a disordered state to an ordered state. However, it is highly improbable that we can go from a disordered state to an ordered state, because there are far more ways, again, to achieve that disordered state. So while it is not impossible to go from disorder to order, it is highly unlikely and highly improbable. So one has to be careful about this. Sometimes you'll see some statements in the press saying that there's been some scientific experiment that indicates that the second law of thermodynamics has been violated. Well, if we use a probability interpretation of entropy, it's not really a violation. If we just simply restate the second law by saying that it's highly improbable that we go from a disordered state to an ordered state, we know that it may occasionally occur, however infrequent and however improbable. It is a very small possibility that this could happen. So this ends our second video on the basic properties and definitions associated with the second law of thermodynamics. In the next video, we'll begin applying the definition of entropy to particular types of processes.